Good morning. I hope you're having an awesome day. I'm sitting here surrounded by the elements on the periodic table to talk specifically about one. That's right, carbon. And the reason why we're going to focus in today on carbon is because, man, it does a great job of doing everything life, everything on Earth, planet Earth, life, everything that is and will be is carbon based. You are carbon based life form. I'm a carbon based life form, but it doesn't end there. It starts with stuff like this: coal. Carbon takes on lots of different forms, even the bright and shiny stuff. That's right, diamonds. Diamonds are pure carbon. Everything around us is made of carbon or combines with carbon. And today we're going to take a deeper dive into carbon. Why, might you ask, are we taking a deeper dive into carbon? Well, I'm glad you asked. I'm going to answer it. Today we're taking a deeper dive into carbon because carbon makes up the foundation of carbon chemistry, and this is where we leapfrog into our understanding of what you'll be concentrating on next year, which is that wonderful voodoo science that everybody loves to talk about. That's right, biology. So, if you have a firm foundation in chemistry and you have a firm foundation in carbon, you're going to have a great start next year when you dive into biology. Let's get going. Carbon, that's what we're talking about today. Let's do a quick review of everything we understand about the atom that is carbon, not just the element. What makes up an element? All the individual atoms of that element. Let's shrink ourselves down to the atomic size and really go over everything there is to know about carbon. So to start with, we know that every atom has a nucleus. Carbon is number 6 on the periodic table. It's number 6 because it has 6 positive protons. Now, it also has neutrons. In this case, it has 6 neutrons. Now, this is where we get that atomic mass. Remember, the mass of the atom only comes into play when you're talking about the nucleus. We don't bother with the electrons. Those are nearly massless compared to these two titans. So we're only going to consider the nucleus of the atom. And so in that case, the nucleus of the atom adds up to 12. That 12 number here, from here and here, that 12 is the atomic mass. Now, the atomic mass is the combination of the protons and neutrons. That's what gives it its heft. Now, that 12 is what's inside the nucleus. Let's talk about what's on the outside. The outside are the electrons. Notice they are negatively charged. You need to have the same number of electrons to balance the positive charge of the protons. So yes, of course, we have 6 electrons to balance out the 6 protons. Now, carbon's pretty special. Let's diagram it here and then really dive into what makes carbon so special and unique. So if we're drawing an accurate depiction of this, what we have over here is going to be 6 little positives sort of tucked around. We've got 3 there. We'll do 3 here. So we've got our 6 positive protons, and now we'll switch gears and do our 6 neutral neutrons. So we've got our nucleus. Our nucleus is shaped. These, of course, are just neutral. I'll leave them as an O. Makes sense. But what we've got to contend with now is to balance out all 6 of these positive proton charges. Now that's where the electrons come into play. And as you know from class and chemistry, as we started off, the electrons make all the difference. They're responsible for bonding. They're responsible for energy. They're responsible for light. They're responsible for a lot of stuff. For not having a lot of mass, they pack a big punch because they have an equal and opposite charge to every proton. That's why you only need 1 electron to balance out the positive nature of a proton. So when we look at this, remember we studied the electron orbital system. Now, on the first energy level, there's only 2 available spaces 4 electrons. That's hydrogen and helium on the periodic table. So our first energy level can only hold 2 electrons. So we've got a negative electron here and another negative electron here orbiting close to the nucleus. But the valence shell. Remember, the valence shell just was a fancy way of saying outermost. The outermost energy level is on the outside, the furthest away from the nucleus. And carbon only has 4 valence electrons. It has 6 total. The first 2 are on the inner. The last 4 are on the outer. And these become the most important. They're responsible for all the awesomeness that is carbon. So these special valence electrons are the ones that are going to be responsible for all the bonding that carbon's going to do with all the other elements that it's going to come into contact with, including other carbon atoms. Now, if you remember, the valence shell can hold a maximum, can I hear it? Oh, I think I did. 8 valence electrons total on the outermost shell of any atom. Of course, we leave aside helium. It only has 2, but it's, over there being a weirdo. So, right here, carbon has the opportunity to take in 4 more valence electrons. That's what it's waiting for. It wants 4 valence electrons. 1, 2, 3, 4. It already has 4. 1, 2, 3, 4. And so it would max out at a total of 8. Now remember, when we drew our Lewis dot diagrams of this, what that really looked like, and what I'm talking about, is when you take the symbol of carbon, and remember, we place electrons around it accordingly. Now, I've heard this analogy, and it makes a total sense, especially given today's climate. When an electron jumps into an energy shell, it really doesn't want to sit next to the next electron on it. So they space themselves out until they're absolutely forced to be sitting next to another electron. So the first electron goes here, the next electron goes here, the next electron goes here, and the final electron goes here. Now that's carbon. So the valence electrons are how we're going to look at this today. We're going to take a closer look now at what the model of a carbon atom might look like, as if we were messing with it in the lab in a 3D setting. Carbon. This is going to represent our carbon atom today. Now, this is just a black wooden sphere, but it does have 4, count them, 1, 2, 3, and 4 holes, I'm touching them right now, drilled into it enough that we can represent those holes as the unmatched valence electron pairs. We're going to assume this black marble here has all the protons and the neutrons and the 4 valence electrons already on it. So these holes represent the electrons that carbon wants, not the ones it already has. Now, a carbon atom would therefore start to bond with other things. Now, when we bring in a bond, we're going to represent it by this stick. The stick is going to represent the bond. Now, I'm not going to attach anything to the other side of the bond yet, but if we insert the 4 valence electrons, notice right here, and then we have 2 more coming in right here. Now, this would represent a carbon atom that has all 4 of its valence electrons that it needed, giving it a total of 8, but I haven't bonded it to anything yet. That's the key here. We haven't bonded it to anything yet. I wanted to give you an overview of exactly what we're talking about here in a model format, because at the end of the day, carbon does some pretty remarkable things. Like I said at the beginning, it's the fundamental basis of life. Everything that is organic, everything that is life, trees, birds, cats, you, me, everything that you know of that is life form is carbon based on planet Earth. And we're going to take a look at what attaches here best. And the best way to start off talking about carbon is to see how well it attaches to other carbon atoms. Let's add some to the pile here. So we start with our carbon atom. We now understand the model and what it looks like as far as the holes that are in here. What we're going to find is that as we begin to accept the 4 valence electrons, carbon's going to easily bond with other elements. Now, what's typically going to happen is that carbon will easily bond with itself. So, what does that look like? Well, as we take a structure of carbon and we begin to add more and more carbon atoms to it, this is the typical carbon atom shape that is formed. And when you add more and more carbon atoms to this structure, they begin to take on a very similar shape. And as they stack and stack and stack on top of each other, what they begin to form is this. That's right, pencil lead. Now, we know that's not lead. Lead is an element on the periodic table. This isn't lead. It used to be, the name stuck, the material didn't. Because of this little thing called lead poisoning, people decided to replace the writing material inside of a pencil with carbon. And what we call this stuff is graphite. And graphite's really, really cool because it's nothing but pure carbon. And it acts kind of like scales, or better yet, it acts kind of like a deck of cards. See, when you take a piece of paper and you draw on it with a pencil, what you're actually leaving behind is a trail of these carbon atoms that begin to stack and slide themselves across. The best way to think about this is if you had, say, a deck of cards, and you took that deck of cards and began to smear it out like so. At a microscopic scale, that's exactly what graphite is doing. It's sort of just smearing each of these molecules along in a path so thick that you can see them, just like this deck of cards laid out. And that's the wonder that we have in pencils, is that we have this material that can be easily laid out, but at the same time, that's also why when you take something abrasive to it and push against it, you can easily erase it. And that's what makes graphite so cool. It's a very specific structure of carbon. So, let's look at what other things carbon can make. So right here, we've got a pentagon-like shape arrangement of carbon atoms, all 5 of them together. Now again, the firm foundation of our carbon to carbon, just like this carbon, is going to be this structure, okay? So what we're looking at here is the basic combination of carbon atom arrangement. What happens when all the atoms start to fold in on themselves instead of laying themselves out flat like our former graphite? Well, sometimes you get shapes like this. Now, what happens is this will come in and bond with these other carbon atoms, like so. And what you get is starting to look kind of like a sphere. Now, the sphere of carbon atoms, turn it on the inside, you can see it from the inside here, is called a fullerene. Now, fullerene, as you can see there at the bottom, is actually short for Buckminster fullerene. Now, that would be a complete sphere. And what we also call buckyballs, or named after its founder in 1985, in which these tight-knit carbon groups started forming these little spheres together. Now, what's really cool is you can start to stretch these spheres out. And as you stretch them out, you can cut one end and the other off. And what you've essentially got is a long tube. And that tube of carbon are what we now in modern age call carbon nanotubes. And they can be grown in a lab, and these right now are going to be some of the cutting edge technology that we're going to be using, these carbon nanotubes. Very small, tinier than a human hair, but they are thin and strong and conduct electricity very well, along with this kind of technology. What we're looking at is to increase computers and their computing power using this very fundamental element, carbon. Carbon is pretty remarkable, I'd say. Let's look at one last structural outline that carbon gives us. Diamonds. That's right, diamonds. And then you can look at that and say, that's pure carbon. The same way that this coal is pure carbon. The same way that this pencil is pure carbon. And the graphite inside. All three of these would be carbon. Now, let's focus on the pretty shiny one. Carbon that makes up diamonds has a very interesting shape. In a geologic sense, we would call it a network solid. By that, I mean it takes on sometimes our typical pentagon-like shape, but also sometimes it takes on this more interesting hexagonal shape. So we've got 6 as opposed to 5. Now, when the 5 tries to come in and interlock with the 6, we get a very interesting shape, because really any side of this 6 would only need 3 more. So you would have it come in and interlock like so. And as it does, you start to get this overlapping pattern of 6, then 5, and you would continue that pattern 6 and 5 and 6 and 5 around to form a diamond. So really, carbon has this remarkable way of making itself take on different forms and different shapes. And it's doing so strictly by itself. There are no other what we would call contaminants. There's no other inclusions in any of this that would cause it to not want to bond with just plain old ordinary carbon. And that is what we're going to continue to focus on. But now let's turn our attention to what happens when carbon starts to bond with other molecules. Hydrogen. That's right, the most basic and most abundant element in the universe, hydrogen. That's going to be the focus for the next few minutes. We're going to talk about how hydrogen can bond with carbon to make some pretty remarkable things. Now, I want you to be thinking about going into our review sessions. We talked about reaction types, and the 5th reaction type that we ended up talking about were combustion reactions. And of course, they always started with some kind of hydrocarbon, a hydrocarbon. And we're going to look at the fundamental, basic type of hydrocarbon that you can build. And we're going to start off with everybody's favorite, cow tootsies. That's right, cow tootsies, otherwise known as methane. Let's take a closer look. Okay, everybody's favorite, methane. Now, we start with our basic carbon atom. It has receiving ends to bond with 4 other things. They could be carbon atoms, as we've just finished discussing. Carbon takes on 3 basic forms. Remember, we have our diamond, we have our graphite, and our fullerenes, otherwise known as Buckminster fullerene. We've gone over those shapes, but let's start to bond it with good old-fashioned hydrogen, of course. Now, as I said before, methane is basically cow tootsies. I'm sorry, but that's what it is. It is that rancid smell that you get, but it's also formed with just a carbon and 4 hydrogens. So our hydrogen model looks like this. They're little white wooden balls with a hole drilled in them so that they can accept, remember, 1 valence electron. It already has hydrogen, the basic understanding of 1 proton and 1 electron. That's what's assumed inside here. But it wants only 1 more valence electron, and that's where this comes into play. This would receive 1 more valence electron. So the bond would attach itself here, and the 3 other bonds would all grab up other hydrogens. And we would get a molecular structure like this. Now, this is methane. We have 1 carbon atom, and we have 4 hydrogen atoms. So CH4 is methane. But here's something interesting. We can expand this. Now, methane is a gas, of course, cow tootsies, but what happens if I take off methane's hydrogen, the 4th one, and I bond it with another carbon atom? Now, it's going to end up receiving, of course, we've got our other 4 receivers, other 3 I should say, and all of those would absorb more hydrogen. Now, as they bonded with hydrogen, we start to get another structure here that looks like this. But this is not methane. No, no, no. This is actually ethane. And ethane is not CH4. There are 2 carbon atoms, so it becomes C2, and there are 1, 2, 3, 4, 5, 6 hydrogen atoms, C2H6. And you see we've got a nice line of carbon here. So notice there's a pattern here. I didn't change anything back here. This is ethane. We started off with methane simply by having 1 methane molecule, and what happens is another methane molecule would come into play, and it would say, wait a minute, I don't want that hydrogen, of course. I want to bond with that carbon because it's nearby. And now we have a hydrocarbon of ethane. You know what? Let's keep going here, because all we need to keep adding really are more methane molecules. Now imagine if this ethane molecule ran into another methane molecule. It might just say, well, forget you, hydrogen. I'm going to instead bond myself to this other carbon, of course, methane molecule. But now, if you're looking at this atomic structure, we have no longer made ethane. What we actually have, and you'll be very familiar with this if you like grilling out on the weekends, is propane. That's right. We've made a molecule of propane. And propane, of course, has 1, 2, 3 carbon atoms. So it becomes C3. And if you're looking, the 2 on the end each have 3. 1, 2, 3, 4, 5, 6. But the central one, it's bonded to the other 2 carbon atoms, so that takes up 2 of its bond placements. And now it only has room for 2 more, so it only has 2 extra hydrogens. So you've got 3, 6, 7, 8. So this becomes C3H8 for propane. I think you might be able to start to see a pattern. What do you think's going to happen? Well, let's take another another carbon atom and bring it to the table. And if we do that, this methane molecule would come in and say, hey, I want to bond with you guys. So it would kick out one of the hydrogens. It would bring itself in. It would then bring itself with more of the hydrogen atoms, and it would make another link. Now, this is pretty interesting. Let's zoom out here a little bit. So, what I find interesting here is that all we've done is we've added, now instead of 3 carbon atoms, we've added a 4th. So, we've gone to C4, and we have hydrogen here. So you have 3 on the end, 3 on the end, 2 in the middle, 2 in the middle. So 3 and 3, 2 and 2, we get a grand total of 6 and 4, so we've got 10. C4H10. No longer is it propane. You've now got butane. So butane is formed with what we call a hydrocarbon chain. All of these are really. The central one, the methane molecule that we started with, only had 1 carbon involved. But notice every time we add a carbon, it adds another link in the chain. And we started off with methane, we moved on up to ethane, we've gone to propane, and now we're at butane. And I want to show you some symmetry here. If we push this aside, when we look at what those actually start off with, we had methane, and that was CH4. All right, so we had methane at CH4. Then we add another carbon. It brings to the table some other things. That was ethane. That was C2H, that's right, 6. So we added 1 carbon, we added 2 more hydrogens. Then we moved on from methane to ethane. We went to propane. That was C3H8. Interesting. And then finally, where we stopped was butane at C4H10. Now, there's a pattern here, and I know you can see it. 2 things. Number 1, in the name. In the name itself, notice the endings all are anes. All right? Now, what this is telling you is that there is a hydrocarbon involved. And a hydrocarbon is made up of just exactly that, carbon and hydrogen. Now, the base for all of this is the methane model, C1H4. Of course, we don't write the 1. CH4 is the molecule. But then, as you add 1 carbon, so carbon was +1. Every single time you added 1 more carbon, 1, 2, 3, 4, etc., you also start off with the base model of hydrogen at 4, 6, 8, 10. Of course, this is add 2. And the names change, but all we're really doing is making a link, a long chain link of carbon atoms surrounded by cap ending with 3 on each side, and everything in the middle still has 2 on each side of hydrogen. This is what we call a hydrocarbon chain. And all of them are gases, and all of them, as you might recognize, are flammable. So that's what makes them key in any combustion reaction. Carbon is at the heart of it all. Whoa, hold on a second. We've been talking about hydrocarbons that are in a chain link. That's great, and they've been making some very familiar things. Our methanes, our ethanes, our protanes, our butanes. But we haven't talked about really what an isomer is. Now, an isomer is when one of these hydrogens and carbon combinations does not necessarily bond in a straight line. So you don't get that chain link. You still get the same chemical formula, you just don't get the same chemical structure. Here's what I mean by that. Let's take a closer look on the board. So, here's our butane. It's in a nice chain link. The carbons are connected. They're not necessarily straight, but they are single file. So, what we're going to look at is what happens when we start off actually with propane, so we would start off with a propane molecule, and along comes a methane molecule. Now, normally speaking, what the methane would want to do is replace this hydrogen. Of course, it would say, I don't need you, and here I come, and I'm bonding at the end, and now I've made a butane hydrocarbon. Great. But on occasion, as that methane molecule comes in to meet up with this propane molecule, in some cases, it won't come in on one of the ends. It might actually come in the middle. So what it will actually do is come in and bond here. Now, if you take a close look at this central atom, it's already bonded to two hydrogens, and it's now, two carbons, and it's also bonded to two hydrogens. But if this methane molecule comes in and wants to attach itself, it's going to take the weakest bond here, the hydrogen, out and rejoin itself with the group. Now, if you look at this molecule, it no longer resembles a chain. In fact, what we have is a nice lattice structure that's no longer in a chain, but it's still a nice network. So, if you count it off, though, what we've still got is our original butane formula, but not the shape. So butane comes in this nice linear chain link. This is an isomer of butane. An isomer of butane is called isobutane. And in this case, we still have our 1, 2, 3, 4. C4, and we need to find 10 hydrogens. So 1, 2, 3. The central one only has 1, so there's 4, 5, 6, 7, 8, 9, 10. So we still have our chemical formula structure of C4H10, but it's no longer in a physical chain link. So it's not butane exactly. It's isobutane. So they have different chemical properties because of their different physical composition and the way the atoms arrange themselves. That is what an isomer is. We need to make sure that we understand a huge difference right here, right now. There are two types of hydrocarbons in the world. The first type is a saturated hydrocarbon. Now, that's exactly what we've been talking about this entire time. If we go back and visit our old friend Mr. Ethane here, what we've got are two carbon atoms bonded together, and surrounding each to fill the rest of the valence shells, we've got hydrogen. So it's C2H6. But one common factor, whether it was methane or ethane or propane or butane, it didn't matter. Even the isomers of it didn't matter. All of them had one major thing in common. They all had single bonds. So what I mean by that is every atom is connected to another atom only through one bonded electron. That's huge. That actually is what defines a saturated hydrocarbon. Let's write it down so that we don't forget. So, a saturated hydrocarbon is going to be defined as single bonded. Only a single bond. The way you're going to know which is which, even if it comes down to the isomers, is that the last part of it, methane, ethane, isobutane, all of them end in A-N-E. That's the suffix on the end of the word. So you'll know it's a saturated hydrocarbon because, and which that means is that they all have single bonds. You'll know it's one by the name as long as it ends in A-N-E. Now, I chose ethane for a reason. Because ethane, and this all has to do with the crazy wacky nature of carbon itself, can do some pretty remarkable things. I can take ethane and remove two of the hydrogens from it. What that leaves open are two empty spaces. And these carbons are going to bend themselves and form another bond. Now, I can't do it with this rigid model of using sticks, but wait. I can do it with springs. So, if I take these bonds and I bend them, what I end up with are double bonds. Now, because we've stepped into a whole new bond type, double bonds means that it cannot be a saturated hydrocarbon. That's right. We're now over into what an unsaturated hydrocarbon is. And in this case, what we're dealing with is not ethane, it's ethene. So let's take a look at what that means. First and foremost, there are going to be three types of unsaturated hydrocarbons. So let's write them down. The first type, number one, what we're dealing with are alkanes. A-L-K-E-N-E. And an alkane is going to only be with double bonds. So if you've got a hydrocarbon, which is what this is, remember, carbon and hydrogen. If you've got a hydrocarbon that has double bonds in it, yes, I see singles here, but if it has a double bond in it, it's going to be considered an alkane. And remember, alkanes are double bonded molecules, just like this. And this is ethene. And that's going to let you know that it ends, alkanes always end in E-N-E. That's how you'll know it's a double bonded, unsaturated hydrocarbon, just like this. But there comes a time when we look at this molecule and say, that's great. We've got a very strong molecule here. But there comes a time when the carbons become so powerful and so needy for another bond that they will get rid, that's right, of two more hydrogens. And in the process of getting that, they've left exposed two more valence electrons that need to be occupied. And that's right, they will then bond with each other by bending and creating another bond. And that doesn't make it a double, it makes it a triple. So now we have two carbon atoms triple bonded with one another and only two hydrogen atoms on the end. So notice the one constant here is that we started off with our ethane molecule, C2, and we still exist as C2. Even as an alkane, double bonded, it still had two carbon atoms. This also has two carbon atoms, but it can't be defined as an alkane anymore, okay? It's a slightly different word, but it's going to do the same exact thing. It's going to describe a triple bond, and it's going to give us a way to understand it by its name ending. But it's not alkane, but in this case, we're not going to call it alkene, we're going to call it alkyne. So you want to say the second one is A-L-K-Y-N-E. Not a big difference, but it does define the fact that we're talking about a triple bonded unsaturated hydrocarbon. So in this case, we have a triple bond. And it's going to end, and you guessed it, Y-N-E. So, we've got some things here. We've got some endings of words that help us identify what type of bond we're talking about. And what we're looking at, and I've kept it in a common thread, is one particular type of molecule that only has 2 carbon atoms. When we were over here, we were dealing with ethane. All right? Now, ethane had 2 of its carbon atoms and 6, and we were dealing with ethane. A-N-E, and that was C2H6. Right there, little guy. C2H6. So this all was C2H6 ethane. Everything's single bonded. That's the key. That's what makes it saturated, that the bonds are in their singular form. No one atom is bonded back to another atom twice. But we move over here, and what we've got here are alkenes. All right? Now, in this case, we take our single bond and we turn it into a double bond. 2 carbon atoms with 2 hydrogens off of each. And this molecule, C2H4, becomes ethene, because we need to, not ethane, but this is ethene. All right, the ending right here tells you it's a double bonded unsaturated hydrocarbon. I know it's a mouthful. Now, what we need to do is make ourselves some more room here, and let's take a final look. If you need to pause it, go back, rewind, you can pick that up again, but let's look at the alkynes, okay? They are triple bonded, so in this case, we have 2 carbon atoms again, triple bonded with only 1 hydrogen attached to it. So this is C2H2, all right? Now, this one's got an interesting story. If you're familiar with welding, of course, you need a torch, something that is going to be very powerful. Oh, and I should probably write the name down, by the way. So this was E-T-H-Y-N-E, ethene, okay? Now, this particular molecule has a triple bond carbon atoms held together. That's a tremendous amount of energy. You can imagine playing Red Rover, right? And you'd all stand in single file lines holding hands. Now, when you play Red Rover, in that case, you would all be in a single chain link. You'd all be saturated hydrocarbons. Now, of course, if somebody were to try to run through you and your friend holding hands, but then all of a sudden you and your friend reached and grabbed with 2 hands, you'd be double bonded to that person. It'd be twice as hard to run through your arms. So you would be unsaturated at that point, and you would be in this double bonded department. Of course, we don't come equipped with 3 arms, but if you can imagine now having an extra bond between you, it increases that energy holding you together tremendously. And in this case, when you try to break apart the bonds of a triple bond or a double bond, it's much more difficult than it is to, say, tear these apart. These are easily torn apart, and they're used as our fossil fuels all the time. We have natural gases, you have gasoline, we have coal. All of these things are types of fossil fuels, and they easily combust. But over here, when you get into things like this, these can be burned as well. But when those bonds break, they release a tremendous amount of energy. For example, welding again. If you are a welder, you need a torch. And one of the most common types of torches is an acetylene torch. Now, notice the Y-N-E ending. Well, there was this French guy, a long time ago. Like Miss Saint Germain might get a little mad at this, but his name was Henri Louis Le Chatelier. And he comes up with this observation that he made, that hydrogen burns at a very specific temperature, but that when he burned a specific molecule, in this case ethylene, what he gets is something that burns at over 1,000 degrees hotter than hydrogen would burn. Tremendous amount of energy. And what's really going on there is that, where's the energy coming from? It's in the breaking of 3 bonds instead of 1 for every single molecule. So you get a tremendous amount of energy release here. You get a pretty good amount of energy release here. But over here, you get very little, and that's only because they are single bonded. Now, hopefully with this, it's a lot. You're taking notes, I'm sure, but with this, you now have a basic understanding of carbon chemistry. The carbon atom is where we started, and we now break that down into what is a saturated hydrocarbon once we started to add other things to the mix of carbon, and we'll be adding other things next week as well. But over here, we start to see the different configurations that carbon can do with even things just as simple as hydrogen. Not to mention the fact that saturated hydrocarbons can still be single bonded, but also rearrange their physical geometry to be an isomer of themselves. They'll maintain, just like I did with butane earlier, they'll maintain their chemical structure, but they will alter their physical structure. And with that, it gives them different properties altogether, which allows us to do different things with, say, difference between butane or isobutane. And this is how we're rounding up our start to carbon chemistry. Okay, one more unsaturated hydrocarbon to go. We've got our friend here, the aromatic hydrocarbon. The symbol is a hint to what we're about to do. It's a little bit complex, but it's okay. It takes on the same shape as our alkenes, the double bonded unsaturated hydrocarbon, but it does something really interesting with its double bonds. Let's take a closer look just to see what I'm talking about. So one of the most familiar structures you're going to see is something related to what we call a benzene ring. E-N-E. Now benzene, remember, E-N-E is telling you those double bonds are present. So what we're going to look for is a hydrocarbon that makes this formula. It's actually C6H6. Now, I drew a picture a second ago that looked very similar to this. What we have here is one bond, double bond. Whoop. One bond, double bond, one bond, double bond. Now, looking at this picture, it doesn't make a lot of sense, but this is sort of the picture that chemists were struggling to figure out for a very long time, because this molecule, benzene, was very difficult to understand. We finally got our heads wrapped around it, and this is the shape it made. So C6H6 is right here. What we're looking at is 6 hydrogen. We can turn it this way so it'll look like our picture here. So what we've got, sorry gang, let me fix that for you. So what we've got is a single bond, but then a double bond, and a single bond, then a double bond, a single bond, then a double bond. There are 3 double bonded carbon atoms attached here. And what that does is it actually bends it into a ring. Bending it into a ring makes it a benzene, E-N-E, benzene ring. And it has 6 hydrogen atoms attached to it. Now, what makes this molecule so special and should be so familiar to you is notice that at the beginning I called it an aromatic compound. Now, an aromatic if you look at this word on its own, aroma, think about it. That's where it gets its name. The aroma of something indicates the smell of something. And an actual aromatic compound typically forms a ring. And it's a nice shape. And what it does, let's say you're walking by and there's a mint leaf over, or a mint bush. If you ever have had fresh mint, it's really amazing. The plant is phenomenal. But its leaves smell exactly like mint. And the reason why you can smell that is because these little molecules might attach themselves. If a hydrogen is removed to something else, some other molecule would come in here and take its place. And then the ring itself would sort of float away. And as it floated away, the aroma would be detected in your nose. And that aromatic compound is identifiable as the smells that you smell. It's pretty amazing. This molecule right here is responsible for the majority of the things in nature that you can smell that have an aroma, that when you lean in to smell a flower, or when you start to cut open fresh basil, any of that kind of stuff is going to be releasing aromatic compounds. And this is the base structure for them, a benzene ring with C6H6. So speaking of carbon, now that you know a lot about what carbon is, this is Bauer, just wanted to say hi, but he's made of carbon too. I'm made of carbon, you're made of carbon, and hopefully you have a much better understanding of what carbon actually is. Now, can you say hi, Mr. Bauer? Say hello. Hello. Ooh, okay. Bauer wants to go back. But remember, it really has to do with just about everything that's living. And remember, even fossil fuels, the stuff like coal, stuff we burn, things like gasoline, are all based on carbon, because the things that were carbon alive are now carbon after they're gone. So we're going to start this journey into carbon chemistry. But just remember, everything we talk about with carbon is going to be building you towards a better understanding and foundation to start that wonderful world of voodoo science, biology. So go ahead, move past this. Once you're done with this video, go ahead and look at your homework that I've put there for you. It's going to be due tomorrow, Friday, by noon. So make sure you get that done. And as always, remember that you are surrounded by people that loved you, and you are always loved. See you next time, gang. Hey, gang, one last afterthought. Just on a side, I thought it'd be kind of cool to wear one of my favorite shirts today. This is the Gemini capsule. It was a predecessor to the Mercury capsule, one of the first capsules that the United States ever built to send humans into space. The only problem was the Mercury capsule could only send one human. This is an artist's rendition and takeaway of the actual Gemini capsule, which was allowed to take 50% more, 2 people into space. They didn't really modify the exterior that much. They kept the Mercury capsule the same. What they did do were scientists were able to engineer a way to remove about 50% more of the space on the inside, which made it a much tighter squeeze for the 2 astronauts inside of the capsule. And they weren't gone for very long. These were not the capsules that we were testing really to get towards the Apollo missions that would lead us into and onto the moon. But I just think it's pretty neat and wanted to explain it to you before I left. So, hey, have a great day. See you next time. Bye.